Our next topic is convergence of random sequences. So you may say that we already know everything about convergence of sequences. We have studied calculus. We know all the definitions. So why do we repeat this? But there is a problem. When we deal with a random sequence, so with a sequence which elements are random variables, this definition of limit from calculus cannot be applied to a sequence of this kind. So let's have a look. This is the definition of limit of a sequence. You already know from calculus. So if limit of an when n tends to infinity is equal to a, or in other words, if an converges to a when n tends to infinity, this means that for any epsilon, for any positive epsilon, there exists n such that for any small n that is more than this capital N, difference between an and a is less than epsilon. So how can we translate this expression from the mathematical language to our ordinary human language? So this means that you can take epsilon as small, as close to 0 as you wish, and for any value of epsilon you have chosen, all elements of your sequence, starting from element with number capital N, will differ from the limit no more than by epsilon. So you can take 1 over 100, 1 over 1,000, 1 over million for epsilon, and so this will be true. Only this capital N will be different for each value of epsilon, but all elements starting from number capital N will differ from the limit no more than by epsilon. So why now let's say that these an and a, so elements of our sequence and the limit are all random variables, not ordinary non-random numbers, but random variables. So why it is impossible to apply this definition to a sequence, to a random sequence? So because it is impossible to check if this inequality we see here, so I mean absolute value of an minus a is less than epsilon, so if this inequality is true or not. So as an is a random variable and a is also a random variable, so it is impossible to say if their difference, whether their difference is less than epsilon or more than epsilon, because it depends on the outcome of the experiment. So both an and a can take different values, and their particular value depends on the outcome of the experiment. Each time the experiment is done, an and a take different values. And for some values, this inequality is true, but for some it is false. So we cannot say, we can choose n, like we can say that let's consider element of our sequence number 276, but we cannot answer this question. So whether this element number 276 differs from the limit, whether this difference is less than epsilon we have chosen or more. So that is why we need some solution, because actually we know that random sequences can converge. So I can give you an example. Like you can, let's say that you flip a coin twice and you calculate the share of tails. So you divide number of tails by the number of flippings. And then you flip your coin thrice, and then 4 times, and then 5 times, and then 6 times, and so on. So each time the number of flippings increases by 1, and you are calculating a proportion of tails, share of tails. So if you do so, you will see that this sequence you get during this experiment converges to 1/2. So when number of flippings increases, this proportion of tails gets closer and closer to 1/2. So for 10 flippings, you can get something like 0.4 or 0.6 or 0.7, for example, as this proportion of tails. But if you have 1 million flippings, it is almost impossible to get proportion of tails 1.4, for example. It is almost impossible that there would be 400,000 tails in 1 million flippings. So obviously we see that this sequence converges to 1/2. But elements of this sequence are random variables. So if we repeat this experiment one more time, so if we flip this coin 2 times, 3 times, 4 times, and so on, one more time, we'll get absolutely different numbers. But this sequence will converge to 1/2. So every time we repeat this big experiment, we'll get different numbers, we'll get different sequences, but every time we will see that the sequence we got converges to 1/2. So this is how a sequence of random variables can converge. This example shows us that it is a possible situation, so that a convergence of a random sequence is not something imaginary, but that it is something that exists in real life. So we need to describe this somehow. We need some mathematical definitions to show. So how can we describe this situation? And so while trying to solve these problems, mathematicians were very fruitful. So they introduced not the one, but four ways to describe this situation. So a random sequence can converge there are 4 different types of convergence. So let's discuss them. The first is a convergence in probability. So a sequence of random variables is said to converge in probability, and the symbol we use for this type of convergence is capital letter P over an arrow that shows us this limit, shows us convergence. If for any positive epsilon, limit of probability that absolute difference between xn and x is more than epsilon is equal to 0. So that means that you cannot guarantee that xn minus x is less than epsilon. But you can say that probability of this, so this is a random event actually, xn minus x is more than epsilon or less than epsilon. This is a random event. It can either occur or not occur. when our experiment is done. And so you cannot guarantee that this random event will occur, but you can say that probability of its occurrence will tend to 0. So the limit of probability of such an event is 0. So the higher n is, the more close to 0 this probability is. So that is how you are avoiding this situation that you cannot check the inequality. So you say, we will be interested not in the question whether this inequality is true or false, but we will be interested now in probability of probability of truthfulness of this inequality. So another way to describe convergence of a random sequence is a convergence in mean square. So a sequence of random variables is said to converge in mean square, and letters MS are written above the arrow to denote this type of convergence if expected value of squared difference of xn and x tends to 0, when n tends to infinity. So, expected value is mean value, average value. So while saying that expected value of xn minus x squared tends to 0, you say that average difference between the element of your sequence and the limit tends to 0. So the difference itself is random, but you say that not the difference itself, but average value, mean value of the difference tends to 0. So this is also a way to describe the situation we get when a random sequence converges. So another type of convergence is what we call almost sure convergence. So a sequence of random variables is said to converge almost surely or to converge with probability 1. And we use either letters AS over an arrow, or sometimes instead of this AS, they use B equal to 1. So this is read as convergence with probability 1. If the equality you see is true, and how this equality can be understood. So this little omega you see here is an outcome of the experiment. So random variables of our interest are based on some experiment, and so their values, numerical values, depend on the outcome of the experiment. As you remember, actually, a random variable is mathematically defined as a function defined on a sample space. So a function such that its argument is an outcome of the experiment. So here they say that probability of such outcome, small omega, of outcome small omega, such that non-random sequence we get after this outcome occurs, converges to a non-random number. So we also get as a result of this outcome. So xn of omega and x of omega are not random variables, but they are non-random numbers. So when the experiment is done, when the result is known, the outcome of the experiment. So when the outcome is given, small omega is given, then xn is already not a random variable, but a non-random number. So this is a realization of this random variable in case when the experiment it is based on ends with outcome omega. So this equality tells us that with probability 1, our experiment ends with such an outcome that we will get a non-random sequence that converges to the non-random number. So, and here, convergence is understood according to a standard definition from calculus. So, as the experiment is already done, so all random variables realized somehow, so they have already taken their numerical values, we are now dealing with an ordinary non-random sequence. And so we can apply standard definition from calculus to this non-random sequence. So this means that if we go back to our example with this proportion of tails in multiple coin flipping, so this means that probability that we will get a sequence every time we do this experiment with multiple flippings, probability that we will get a sequence that converges to 1/2 is 1. And probability to get a sequence that does not converge to 1/2 is 0. And the last type of convergence is a convergence in distribution, or weak convergence. So a sequence of random variables is said to converge in distribution or to converge weakly. And the notation they usually use is letter D over an arrow, but there are plenty other different notations. So I saw letter F for capital F for the CDF, or letter W for weak, or a handwritten L for law, so distribution law, and so on. So there are different notations used for this type of convergence. I prefer this one, so I prefer letter D, but there are other ones also. So it is true, so we have a convergence in distribution if for any x sequence of CDFs of the elements of our sequence converges to the CDF of the limit. So fxn of x is a CDF of the nth element of the sequence, and fx of x is the CDF of the limit. And so sequence of the CDFs of the elements of our sequence converges to the CDF of the limit. So in each point, in every point, so for every x, this is to be true. And so after we substitute this small x, we also get an ordinary non-random numerical sequence, and so it converges in just according to a standard definition from calculus. So actually, you should what you should know also. You should know a relationship between these types of convergence. So if a sequence converges almost surely, then it converges in probability. If a sequence converges in mean square, then it converges in probability. If a sequence converges in probability, then it converges in distribution. So almost sure convergence and convergence in mean square are the strongest types of convergence. And convergence in distribution is the weakest one. So that is why it is called also weak convergence, because so if there is a convergence in distribution, maybe there are no other types of convergence. So that is why it's the weakest one. So we will use these notations. So later we will discuss some theorems, and in these theorems you will see that a sequence converges in mean square or in probability or in distribution. So I gave you these definitions so for your future understanding of these theorems. But what you should know also about these types of convergence is that actually in practice they all look the same. So if you are observing a random sequence, so if you just make observations, you get some data and you try to analyze to understand what is happening, and you see by your own eyes that there is a kind of a convergence here. So you see that you go along your sequence, and so elements are getting closer and closer to some number that is obviously a limit of this sequence. So you see that there is a convergence, but you cannot understand of which type. Convergence of which type do you have here? So they look like just the same. So you can only understand by just practical observing of this random sequence of your interest. You can just understand that there is a convergence, and you cannot understand convergence of which type do you have. So these differences are actually not for applied mathematicians. They are for theoretical scientists. So this difference is important when you prove theorems, when you are trying to get some scientific mathematical results and so on. So it is not so very important when you are dealing with statistical data, with observations and so on. So this difference is important only to prove theorems, and so I gave you these definitions just as I have already said, for your future understanding of some theorems. So when I will say that some sequence converges in distribution, so you may ask, so what do you mean saying converges in distribution? So that is why I gave you these four definitions. So just to make our course more, how to say, mathematically correct, mathematically strict.